Okay, welcome to week 6. I'm now trying to have a little camera at the bottom, which I'm not used to at all, and I always wander over to the board and point at things with the yardstick. So this is mostly just sort of to test it out. I'm not thinking it will add anything, and it's positioned wrong to look up my nose, but that's the best I can do. Other than that, you can turn in homework now for the saving for retirement, but I would advise against it. We haven't finished the lecture. I owe you something, so I want to go to the lecture notes as our get started warm-up thing for the day and look at our second to last board work when we were talking about percent sentences. Okay, remember this stuff from a week ago? So, Edwin had this thing he called power, P, W, and R with a triangle. There was some way to deal with percent sentences, and it worked when the part was smaller than the whole, when the new amount was smaller than the old amount, which for most things in life work that way. Things go on sale, the new price is smaller. The amount you have left of something is less because you've used some up. Whatever. But not all changes are like that. Sometimes the baseline, the original, is the smaller amount. Your money goes and increases in value. Instead of dieting, you're gaining weight because you're a kid who's growing. Things like that. And his method didn't work when the baseline amount was the smaller number. So I've been playing with it, and I have 2 different shortcut ideas, and I'll show them to you. If you like them, let me know. And if you don't, that's fine. So we had these 2 methods of solving these percent sentences, the translate method and the proportion method. And I'm not going to go over them again, but I just want to use these old slides to quickly kind of justify my shortcuts to you, so I don't have to do all the work again. So, the basic format of the percent sentence was something is something percent of something else. So this was your part, or your original, or your new amount. This is your percent, and this was your whole. Whoops, I said original. I am wrong. This is your change. Oh, this is the original. This is your baseline. Okay. So you could have something like 50 is what percent of 100, and it would be 50%. Things like that. Does this ring a bell? Is this enough review of the setup? Okay, get rid of my... So what I'm wondering is, first, what happens if I'm missing the part? So I'll go back to this lecture. What is 35% of 60? If what we're missing is the part, this part is going to be the what? The part's the what? The other 2 things we're just going to multiply together. See how that shape kind of works? So we could say, if this is what we're missing, then multiply, whoops, not with a highlight. Multiply the percent and the baseline. That's an intuition that lots of people have already. If I'm saying what is 30% of 200, I'll do 0.3 times 200. The next case could be same kind of thing, with the what in the middle. Now I'm not sure what the percent is. 12 is what percent of 5? It's easier to see if I get the, where is it? over here. I skipped past it. So in this case, I have my new, my change, my part on this side, my original, my whole, my baseline on this side. This was one example where the newer thing is bigger. The kid grew from 5 pounds to 12 pounds. And what I'm doing is I'm taking the part number and I'm dividing it by the whole number to get the percent by itself. Can you see that shape happening here? So if I go back to my thing, then if I am missing the percent, then I want to do my new divided by baseline. And I have to do it in that order. If I switch them around, the multiplication isn't the same. 12 divided by 5 isn't the same as 5 divided by 12. The last case was if what I'm missing is the baseline, the whole. And then, to get this by itself, I have to divide both sides by the percent. So what I'm going to do here is have my part, I should call it new to be consistent, new divided by baseline. Whoops, no, I'm just copying. I don't know the baseline. New divided by the percent. So if you wanted something to memorize, then you could just say, here's the 3 cases, and here's which type of multiplication or division to do. In my brain, this is more work. I would rather just have the proportion or the translate method where there's just one process, it always works. I don't have to memorize 3 different things. But if you like gizmos, then this is a reliable gizmo that will work whether or not the new or the old is the bigger number. If I try and make it shaped like a triangle, because that was kind of a cute feature of the other method, I'm going to draw it upside down because to me the baseline sort of should be the base. And then I have a percent, and I have my new thing. So what would happen if you don't know the new thing, then you're going to do the multiplying the other two. I'll start at the baseline, I'll multiply it by the percent, and I'll get to the new thing. Actually, I should color code this. Oops. Did I color code that? No. So that was this one. If what I don't know is the percent, then I'm going to do that, take the new and divide it by the baseline. And if what I don't know is the baseline one, then I'll do new divided by percent. So that was orange, and new divided by. And for me, this is just the worst of all. There's no way this is an easy thing to use or memorize or write on my paper or something. So I have failed. I was trying to make a better cute triangle diagram to improve what Edwin had shared. Because his was, it was cute. It worked as long as the other number was, the new number is smaller. But I just can't. This is like a terrible thing. I can't imagine anyone ever doing this. Maybe you can do better. Maybe you can take these 2 slides home and say, this is the better thing I would do. But I'm not up for it. So if you like this one I could see someone would put in their notes, because you're allowed to use your notes in the class. But I still like the other 2 methods. Teach them. Okay, back to math 25 new stuff. So, saving for retirement, we did 2 parts already thoroughly. We talked about the percent sentences. Blah, 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 blah. And then we talked about what interest was and simple interest. And I can do more of these if you want, but I'm not sure that that's the best thing to do. Interest was principal times rate times time. The features of simple interest formula that were tricky was you have to make the time years. If it gives it to you in days, it's something over 365. If it gives it to you in months, it's something over 12. And you have to remember that it spits out only the interest. If the question asks you what's the total amount to pay back, including the principal, you have to add the principal back on yourself. So that was simple interest. We talked about appreciation and depreciation, only that I said we're going to skip over it. So this is why I skipped over it. This will be a review of the simple interest formula. So this is just words. Sometimes we say that like a painting or an antique car or something appreciates or depreciates. It goes up in value, it goes down in value. And it's the same as the simple interest, except that there's no interest. There's no actual fee being charged by someone borrowing money and someone lending money. So exactly the same stuff works. Let's look at number 39, which is a kind of funky problem. So Scrooge McDuck has $1 million and his investment appreciates, goes up 3% 1 year. So I'm going to ask myself, what is, don't write things yet, 3% of 1 million. If I want to use my shortcut, my 1 plus trick, then instead of 3%, what should I ask? No, that would be going down.
What's the other thing?
If I translate it, yes, I would get 0.03. That's going to give me just the change, right?
Oh, I know. So it's 1.03.
Yeah, so if I do this, then that was my shortcut. Remember way back from a week ago, that if I say what's 103%, the 100% keeps the million around, so I don't have to add it back on at the end, and the 3% is how much it gets bigger. Okay. Well, this is just going to be 6 zeros. 1, 2, whoops. 1, 2, 3, 4, 5, 6. There we go. So that's the appreciation. Then it depreciates 3% the next year. And this is going to be the same kind of thing, but now we're going down. So I don't want to add 3% to 100. What percent do I want to use instead?
97.
Yeah, everyone see why 97 is a good one? If I had 100%, that would keep around my 1,030,000. If I took away 3%, that leaves me 97% left. still look skeptical. I could find 3% of this number and subtract it and do it 2 steps. If that makes more sense to you, go ahead. You can take 2 steps of this. Okay, and the number I want to write isn't 1,000,000 anymore. Now we're starting at the bigger number, because that was what happened at the end of the first year. I don't know what that is off the top of my head. So 99. So Scrooge was surprised. He thought if you went up 3% and down 3%, you'd be back where you started. That seems to make sense. But no, if you go up 3% and down 3%, then you are 900 short from where you were. So why did he lose money overall?
Gets 3% of the 30,000. That's different than 3% of a million. The 3% of a million got you 30,000, but when you have to do it in reverse, you have to take into account that new thing. So it's like compound interest in a way, but in reverse, I guess.
A little bit. I could phrase it that going down 3% means he goes down not only 3% of the million, but also 3% of the extra 30,000. So he goes down sort of from 2 places. Or you could just say the same percent of a bigger number is bigger. 3% of Scrooge's savings is more than 3% of my savings. Okay, and that didn't actually give me a problem that has simple interest, so let's do that anyway. I do want to do a review one. So let's just make up some numbers. How much are we going to get a loan for?
50,000.
50,000. Oh, okay. What's the interest rate that someone's charging us on this loan?
9%.
Oh, okay. I'll pick this one. Let's say that we're borrowing this to whatever, buy a car, a boat, something, but we want to pay it off quickly. We're only going to have 8 months. So 50,000, that's ready. 9%. I can ripple off that. And then 8 months. I don't want it months.
So 8 over 12.
Yeah. So 8 over 12.
6, 7.
Two-thirds of a year. Okay. Now, I've done the tricky part. I can plug everything in. Principal times rate times time they get $2,999.97. We didn't start with a word problem, but remember, this is just the interest. If the problem said, how much does so-and-so pay back at the end of the 8 months, then you'd have to add back in the 50,000. As a side note, when I'm using my calculator in this line for plugging things in, how do I do the 6 repeating? When I write it on paper, I put a bar above it to represent that the 6 repeats forever. But I can't do that in my calculator.
So round it. Or do a couple 6s?
Yeah, just fill it with as many 6s as you can. When you get a repeating decimal, and some calculators will actually understand what you're trying to do. So as a test on your calculator, just to see, try doing 3 times 0.3 repeating. So this is a third. Right? 1/3 is 1 with an infinite number of 3's after this. So this should be 1. And some calculators, when you do this, 3 times point, and then 3, 3, 3, 3, 3, until you fill it up, will do 0.9999999. And others will say, oh, I know you're trying to do 3 times a third, and they'll just put 1 as the answer. Anyone get a 1 instead of lots of 9s? Yeah. So
this is the one they sell on the campus for about $20.
Anyway, interesting. Actually, while I'm there, as a side note, if you have 0.99999 forever, then because of this, you can see that those are actually the same. 3 times a third really is 1 exactly. This one is a bunch of 3's after the decimal place. And if I multiply each of those by 3, I'll get 9's. And they're the same. So 0.9999 isn't almost 1, it really is 1. But that's my math 25. Okay. Any more simple interest requests? I can do more of them if you want. Okay, Thursday we did this thing with 6 years of rent increases. We had this table we developed, and in case you were absent because it was important, then there's this cheat where, look just at the column here on the right-hand side. The first year, it went up with times 1.05. The second year, we take that and we multiply it by another 1.05. So it went up twice, there's a square. The third year, we take this and multiply it by another 1.05, so there's a 3. And the pattern keeps going. However many years, that's the exponent to find the final value of this apartment rent. Does that ring a bell if you were here last week? If you weren't here that class, do you want me to say more? No? All good. Okay. So that kind of pattern is compound interest, and we talked about that. There was another table if you want. But you take the principal, up above it was the 500 the rent started at, and you multiply it by the 1 point, whatever the rate is. Up above it was 1.05 because it went up 5% a year. And then the exponent is the number of times that compounding has happened. I actually can't remember. How many examples did we get to do of this Thursday? I know it wasn't nearly enough. Did we do any at all?
2, maybe, I think.
Have we done 47? Should I do it again? Okay, let's do it. placement is horrible. Okay, so there's our formula. I'm writing it a little differently now that I am freed from having to be looking at a typed version. Oh, okay. And just like before, make that bigger. Then my strategic thing to do is list out all the variables before I start plugging things in. Because plugging things in a formula is easy and the calculator does all the work. The trickiness is if anything needs fidgeting. Just like when we did things a moment ago, we had to fidget with the rate, do some riplaw, and we had to fidget with the months to turn them into years. The compound interest ones are just notorious for there's always fidgeting to do. And I should have been good, do my fidgeting in blue to be consistent on the other slide, but I didn't. Oh well. So I will list out everything. Total amount, principal, rate, per payout, and number of payouts. I'm going to copy all that because I will use that setup again and again. Okay, I haven't even read the problem yet. I just sort of know that it's a compound interest problem because it has the word compounded in it. And so I have to do all the setup. But now I'll read the problem. So the total amount, that's what I'm solving for. And at this point, I'm going to pause and read ahead because the problem could say, what's the total loan at the end? Or it could say, what's the interest? And this formula is the opposite of the simple interest one. The simple interest spit out only the interest, and I'd have to add back on the principal if that's what I wanted. Whereas this formula spits out the total. If it ever asks me only for the interest, then I have to subtract away the principal when I'm done. But in this case, when I look, what's the total loan amount after the first 18 months, then I'm good to go. I don't have to do any subtracting at the end. If I did, I'd make a note there so I don't forget. Okay, the principal was 100. The rate per payout. Well, it's a 3% annual rate. I'll go ahead and do my riplaw. But that's per year. And the compounding happens monthly. So I need to change this yearly number to be a monthly number. Am I going to divide or multiply? Do I have 12 copies of the 3%, or do I have to split the 3% into 12 parts?
You have to divide it by 12.
Wait. Yeah. I have to take that 3% and share it over the 12 months. So each month gets a little bit of that 3%. So that's what I'm dividing. I'm taking it and making pieces out of it. Okay, what is 0.03 divided by 12? Okay, and then 18 months. Do I have to fidget with my 18? What time frame do I want things in? No. That's compound interest. So it's compounded monthly, so I want everything in months. So the 18 is great. It already is months. So now I'm ready to plug things in. What I wrote doesn't look too bad. I have the principal. Ta-da! I put a 1 in front of the 0.0025. There's parentheses up in the formula when I wrote it, but I don't actually need them when I'm using it. I can put a 1 in front easily enough. And then the exponent is just how many tails. Okay, there's a lot on the board right now. Questions about any of this? Okay, we're going to do so many of these. Okay, 100 times 1.0025, exponent key 18. This might be the first time, as you're doing this with me, that we've used your exponent key in class. So everyone, if you haven't yet, grab your calculator and see if your calculator can do this. Okay, look up here for a moment as you're hunting. So there's two styles of buttons. Some buttons say y to the x, and some buttons have a symbol that's called the caret, which is like that. Even if your calculator has a y to the x button, when you look at the screen, it's going to have a caret symbol, just because it can't really do the little y to the x. What you don't want is there's a button that has EXP. That's for exponential notation. Don't do that one. That's a different thing. So you should be able to do 2 to the third power is 8. 2 times 2 is 4. Times 2 again is 8. Make sure you can do that. And if you can do 2 to the third power is 8, then see if you can plug in the problem we just did, get the same answer I did. Everyone's calculator works. Most of these calculators have a secret reset button on the back. So if they're ever stuck, then push your secret reset button.
Yes. Thank you. That's good to know.
Yeah.
Okay, can you go back?
Go back to this one.
So I have the wire. I have that first one, so how?
So 2, y to the x key, 3 equals. Okay, now do this one. So 100 times 1.0025, y to the x key, 18 equals. Yeah, the first time I worked in retail and someone told me you could pop open a cash register with a button underneath, that doesn't sound safe. It's probably not true anymore. It's all computerized these days.
I said which one of the cash register jobs, and I've never had one that could come over with a button
Underneath?
like that. Maybe I did and I just didn't know
No.
it.
This was long ago, Little Caesars. It was a great job when I was 16. So 48 is a reminder that if it asked only for the interest, we'd have to subtract away the 100. By the way, how come it's not 103? If it's 3% of 100, you'd think it would be 103. That's the compounding. Each month it builds a little bit, and over the course of the year, it's equivalent to 4.6% instead of just 3. Okay, let's keep on. So, 18 months, a year and a half. So it should have been $1.50 instead of $1.60. Let's look at a longer term. Okay. It's still true that I'm solving for the principal. Oops, this is simple interest. I don't want to do a simple interest.
Well, it still has to be compounded because it's simple at the end of the year.
No. If it says simple interest, that just means you only get the payout at the end. So we can certainly do that if you're interested in how much extra we get compounding, but I don't want to go back and forth in the middle of the lecture quite yet. Okay, so it's compounded monthly again, so all of my things need to be in months. My rate and my payouts. So the principal is $2,000. What am I going to do with my 0.09?
1/3. No. Yeah. 2 3/4. Would it be better to leave it in fraction form? If we have a calculator that can do that?
No benefit.
Okay.
So same as before, I have to take my 9% and share it 12 times, so each month gets a little bit of that 9%. Now we have 30 years. That's no good. How many times does this person get their payout?
Times it by 12.
Yeah, why am I timesing it by 12?
Because each year is opposed to 30 12s, so you have to have 30 times 12.
Oops,
Each year has 12.
yeah, each year has 12. So I have 30 of those 12s. Everyone okay with my blue stuff? So this pattern is how compound interest works all the time. If it's weekly, you'll have a divide by 52 and a times 52. If it's monthly, you'll have a divided by 12 and a times 12. And so on like that. But as we saw before, it's not always that way. Maybe they just give it to you in months. So you have to be alert. But once you've set it up, now the calculator does all the work and it's not too bad. So I'm going to put a 1 in front of my rate and my exponent. Okay, did I hit a calculator button wrong? Everyone get the same as me?
Is 360 the exponent?
Yep. Because my exponent is how many payouts there are. So there were 360 times that this person got their bank statement or whatever.
So, in this case, would we go 2,000 times 1.075 and then that answer to the exponent, or is it?
No, because we're not raising the 2,000 to the exponent, so you can't hit equals right there. Your calculator knows order of operations, so it will say the exponent applies first, and then the multiplication does. Everyone's calculator agrees, because you're going to have to do this at home, so. Okay, sometimes what people do is follow the order of operations themselves, because they're, if I had the 0.09 divided by 12, 0.0075 on the screen to look at, then I can just say plus 1 to give me this part. Do the exponent first. Whoops. Exponent. And then do the multiplying. So if you are someone that likes to do just a little bit and hit equals and a little bit and hit equals, you can do that. But it's probably easier to just do the whole thing. Okay, is it okay if we go back to simple interest? Do you want to see how this has more interest than the simple interest case? I think that's a nice question to do. I just didn't want to jump back and forth to simple interest too much before. Bigger. Oh well.
Oh, so you're just going to take the 9% times it by 30.
Yeah.
Since it's simple interest.
Whoops, I forgot principal. That's going to be the same, isn't it? So remember, for simple interest, you always want everything to be in years. That's how the formula is designed. In this case, they were. Everything is good. Okay, so the simple interest is just 7,400, which is a lot less than, what was it, 29,000 we had before. So over a long time frame, the compounding really helps. Oh, okay. Most things in life will compound monthly. That's how your credit cards work. That's how your bank accounts work. But there are other ones. So some things just compound once a year. Monthly we've seen as 12. Quarterly would be how many a year? 4. Weekly? 52 weeks in a year. Semi-annually is twice a year. Semi-monthly is twice a month. So 24, twice the 12. And then bi-weekly is every other week. So half of the 52 is 26. You're probably not going to see some of those ones at the end of this chart much, if ever, in real life, but just as like a heads up, you might sometime. Annually happens a lot. Monthly happens a lot. And quarterly, most stock dividends are quarterly. So people that invest will see quarterly things. Okay, going back to our theme about how to write things, some people like the formula we've been using. They don't mind that the compound interest formula is a little bit vague and just says per payout and number of payouts. Other people don't like the vagueness, and that is fine. And so they're going to memorize a set of formulas or have in their notes. They'll have one for annual. They'll have one for monthly with the divided by 12 and times 12 put in. They'll have one for quarterly with the divided by 4 and times 4 put in, and so on. So if that makes more sense for your brain, then that is fine. You can have different formulas for the different amounts of compounding. If you're okay with the generic formula, then that works too. I'm just going to take a screenshot for the notes on that.
That's on the page right under number 51.
I don't know. Let me see. What was above it? Yes, right under 51. So if you like that, do that. Lots of students do that. Okay. That I will save for our review next time. So, we have just enough time to talk about the rule of 72. Has anyone heard of the rule of 72? No. Okay. So, in real life, sometimes we just want a quick and easy estimate. How long till we get rich? Right? Whatever. So, imagine that you have $1,000 in an account that earns 10% interest every year and is compounded annually. How long will it take to double your money? We're running low enough on time, I'm just going to show you the answer. The 1,000 is always the principal. It's always 1.1 because it's 10%. So all we're changing is the exponent. 1 year, 2 years, 3 years. When do we double? A little bit after the 7th year. That make sense?
That's only for 7% interest?
10% interest, 1.1.
And that's why it's 0.1?
That's why it's 0.1, because it's 10%. I just don't want to do that many problems. If it was 7% instead, we could do the same kind of thing. Now it's 1.07 in each row. And we could do the formula all those times, and sometime after our 10th row, will have doubled. Sometime during year 11. And so on. There's a little cute, colorful chart here that summarizes this. We'll do lots more examples of compound interest on Thursday and probably Tuesday also. But just sort of as a summary, at 3%, at 6%, at 12%, here's how much you can have. And there's a pattern that if I take the percent and the years and I multiply them together, and I'm using the percent as a whole number, I'm not rip-flopping it, then when that is 72, it doubles. 3 times 24 is about 72. 6 times 12 is about 72. 12 times 6 is about 72. We have 10 and 7 is about 72. It's not an exact thing, but if you just want a quick estimate, how long does it take an investment to double? How long does it take an antique car to appreciate and worth double as much? Then when the percent increase and the years multiply to 72, it's going to double. So, if you think about that, imagine you invest $1,000 at 2%, compounded annually. How long will it take you to double your money?
36.
36, yeah. 36 years to double your money. You're not going to retire on that. If you had $1,000 and you spent 10%, how long till you have half left? To double it would be 7 years, as our rounding estimate. Then is it going to work out the same way? It actually does. So it works for getting bigger, it works for getting smaller. There we go. We have a minute and a half. The last formula, which we'll get to on Thursday, is called sum of annuity due. It looks worse. In fact, I have to shrink this a little bit in order to fit it on the page. It's a longer formula, but it's not actually any worse, because all you have is the principal and the rate in the years. It doesn't have more parts. They show up more often, but there's only the same number of parts. And it's actually nicer, because we will only do it with years. There's none of this divided by 12 times 12 shenanigans. So I'm not going to do an example now, I don't have time. But this formula is the case where we deposit money again and again every year. Every year, Amanda puts $500 in her savings account. Something like that. So in real life, none of these formulas are accurate. We save a little bit when we're young and don't have any good jobs and careers going. And as we get older and get more financially established, we save more. No one puts the same amount in every year all their life. But if we're just trying to kind of do some ballpark estimates, then this is the other formula we need. And the last puzzle piece will be putting them together. So some years you just put in some and save. Some years you keep putting things in. How does it all come together? So that's our prediction, or heads up for what's coming later. Okay, any questions? Okay.